Imagine yourself in motion, whether it's making the hike up Freshman Hill every day, strolling through the cold to find an open chair, or running to the gold bus to make sure you aren't late to class. Through all these actions that we experience on campus, at the center of it lies intricate movement orchestrated by your body. Every step, leap, or twist seamlessly coordinated by a marvel of biomechanical engineering. Human mobility, essential to our existence, is a dynamic interplay of bones, muscles, ligaments, and nerves. At its core is the hip joint. From walking and standing to running and jumping, the hip joint is essential for transmitting forces efficiently. Its intricate design combines stability and mobility, but the hip's significance transcends mere movement. It maintains balance and posture, impacting our comfort, quality of life, and emotional well being. Nevertheless, the relentless toll of wear and tear can lead to the erosion of hip function, robbing individuals of their mobility. Osteoarthritis, characterized by the gradual degradation of hip cartilage, and a vascular necrosis stemming from compromised blood flow to the bone, stand as the two prominent causes behind hip joint deterioration. These conditions exact a profound toll on individuals' quality of life, emphasizing the critical importance of hip replacements. The imperative to design and manufacture hip replacements is underscored by the imperative to restore mobility, alleviate pain, and ultimately enhance well being. In our exploration, we shall dive deeper into the intricate mechanics governing the hip joint, unraveling the complexities that require the necessity for innovation and precision in hip replacement manufacturing.
The hip is a simple yet important structure in our bodies. Medically, the hip will include not only the bone structure, but also the muscles, veins, and connective tissue that enable its motion. In terms of hip replacements, however, only the bone portion is relevant. The joint itself is made up of the femur bone and the socket in the pelvis. The end of the femur has a protrusion with a ball-shaped bone at the end, called the femoral head. The femoral head fits into the socket in the pelvis, called the acetabulum, and the head is attached to the femur with a segment of bone called the femoral neck. Both the head and the acetabulum are lined up with smooth cartilage called articular cartilage, which helps the bone slip smoothly without damaging or wearing down either side of the joint. The cartilage is also meant to absorb shock from movements. The cartilage is thicker towards the top of the socket, where most of the forces occur during walking or running. The joint itself is held together by surrounding muscular tissue and the tendons that attach the femur to the pelvis. The hip replacement itself is not responsible for maintaining a lock when the joint is in tension, but needs to avoid slipping out of the socket during compression. The forces on the hip joint are a function of body weight, and the peak reaction forces at the joint are commonly many times someone's body weight. According to the paper, Characteristics of Hip Joint Reaction Forces during a Range of Activities by Layden et al., the hip withstands forces ranging anywhere between half to 9 times a person's body weight tested across a variety of common motions, with sitting to standing having the highest average peak reaction at 6 times body weight. The joint also needs to remain inside the socket without slipping out. The same paper measured most physical activities to have a peak impulse of around 3 times the lower impulse of walking. This is easy for the biological joint to accommodate since the acetabulum is considerably wider than the femoral head and rather deep. But most hip replacements are much smaller and have sockets that are not quite as deep, raising some interesting design considerations.
Let's talk about the design of a hip replacement part. Hip replacements offer incredible opportunities to patients to regain their mobility and range of motion, and their design is crucial for success. The most important aspect of a good design is that our replacement part can fully replace the job of the original hip. Since there is no one universal part that would perfectly fit in every patient's body, most of the time, off-the-shelf parts that come in a variety of standard sizes and shapes are used for replacement surgeries. However, they may not be perfect for everyone, especially for athletes that want to regain 100% of their ability to run, for example. We will talk about how surgeons design a perfect part for a patient later on in the video. Now let's take a look at a 3D model of a hip replacement part. This model, right here on the screen, showcases a hip replacement part. It is made of 4 different parts: the femoral stem, the femoral head, a polymer liner, and a cup socket. Zoom in. This is the place where our femoral head is able to freely rotate to accompany the movement of the leg. At a closer look, we can see there are 2 different layers of the cup structures here. The purpose of our second layer here is to reduce wear. The socket cup is mostly made of metal. Therefore, Adding a buffer layer of plastic liner is essential for the longevity of the parts. Here on the screen, we have a scaled-down 3D printed model of a hip replacement part. It might seem pretty straightforward to create a model like this. One common parameter that needs to be considered are the femoral head sizes. Here's a photo of different sizes of one of the manufacturers of hip replacement parts, Zimmer Biomet offers. It ranges from 22 millimeters all the way to 40 millimeters. To personalize the perfect fit, surgeons use detailed imaging scans such as CT scans or MRI scans to create 3D models of your unique joint anatomy. On top of the femoral head size, the length or the angle of the femoral stem can also be altered. Now, let's take a look at the manufacturing process of our hip replacement part.
One of the most important aspects of the implant is that they're designed for biocompatibility. With this in mind, several material options are available. For metal parts, materials like aluminum, stainless steel, cobalt chromium, or titanium can be used. For plastic parts, materials like PTFE and acetal are common. And for wear surfaces, materials like ceramic or zirconia are preferred. Today, most implants use titanium or cobalt chromium for the femoral stem and cup socket, zirconia for the femoral head, and PTFE for the liner, which you can see rendered here. As mentioned earlier, these parts sometimes have the need to be custom tailored to existing body geometry, which plays a large role in the design for manufacturing. To achieve this customizability while maintaining precision, parts are normally machined from billets. While this process is slower than something like casting, the cost and time savings in the long run from being able to easily modify geometry on a part-by-part basis drastically offsets the time loss. Another benefit to machining is that it's easy to recycle any waste material from the process. After machining, both the femoral stem and cup socket are polished before a textured coating is applied that allows them to better adhere to the cement securing them to the bone. The femoral head and liner are also polished, but instead of being coated, they are lapped for a smoother surface finish. After this, the head is pressed onto the stem to complete the implant. During the surgery, the stem and head assembly is cemented into the femur, the cup socket cemented and screwed into the hip, and then the liner placed in between to reduce friction and wear.